Good afternoon, everyone, and welcome to this afternoon's second workshop in our NABERS Energy Simulation series. Just going to give a couple of minutes just to welcome everyone into the session, and then we can kick off from there. Great to have everyone in this lovely sunny afternoon. I'm based in Sydney, so it's nice and sunny today. And just allow a couple more minutes just to have great to see there's a lot of people joining us today. So if we go on to the next slide, I'll just go into some general uh, uh, welcoming to our panelists today. So my name is Ryan Flack. I'm the New Builds and Planning Sector Lead here at NABERS. And I am joined today by PC Thomas and GS Rao, both from Team Catalyst. Both are on our NABERS Independent Design Review panel and have quite significant experience in our building industry and have countless NABERS Commitment Agreement RDR reviews under their belts. So I will hand them over to them later on in the session to present, but I'll just go through an acknowledgement of country to welcome us in today. So I'd just like to acknowledge the traditional custodians of the lands that we're joining from today, and acknowledge the Aboriginal and Torres Strait Islander peoples and that are First Peoples and traditional custodians of Australia and the oldest continuing culture in human history. We pay respect to elders past and present and commit to respecting the lands we walk on and the communities we walk with. And I'm joining today from Gadigal land. And we'll just go to the next slide as well. And so for the presentation today, we've muted all the participants to prevent any sort of background noise coming through. The session today will be recorded and will be available later on as well on our YouTube channel. And we will be sharing the recording as well following the session. And if you would like to submit a question as we go through this webinar session, please make use of the Q&A function that you can see on your screen. And we'll be taking questions throughout and having a question and answer session following the conclusion of the presentation. So without further ado, I'll hand it over to PC and GS Rao to present the next couple of slides for us.
Good afternoon, everyone. This is GS Rao. Welcome again on this bright sunny afternoon, as Ryan mentioned. This is the second of the webinar session that we are conducting today. The first webinar session, which Ryan covered earlier on May 8th, essentially covered the NABERS Commitment Agreement process. It covered the NABERS Agreement to Rate process, the National Construction Code that delves on J1B1 pathway, the New South Wales SEPP requirements that was discussed in webinar session 1, and also some current incentives that is available for commitment agreement ratings. So that was essentially part of the webinar session 1. And today, what I would like to cover, hopefully this afternoon in this session, is to cover the following topics: give you an understanding and an overview of the types of green rating systems in Australia. Also walk you through current commercial building rating systems in Australia relating to energy greenhouse gas ratings. Discuss compliance stringency for the type of rating and the administering body. We will try and unpack the nitty-gritty of the simulation process and complexity involved, and essentially where simulation tools and the requirement of simulation intersects with the ratings. And then we'll close off with a question and answer session, as Ryan mentioned. So let's go on to the types of rating systems. And essentially, there are two broad channels of rating systems. One is what we call as the design or attribute-based rating system, and which uses a predicted building energy or greenhouse outcome. So which is a design or attribute-based rating. The next one, which essentially looks at, is an operational performance or a measured, declared, or outcomes-based rating system. So essentially, it's for an existing building. It's a performance-based rating system, could be measured, declared, or outcomes-based. And both these schemes, essentially, rating systems, are could be either voluntary or it could be mandatory. So the design and performance rating systems could fall into the category of being a voluntary system or based on a compulsory or a mandatory based system. And if you look at the next slide, where we talk about the types of rating systems for commercial buildings, essentially, the rating system for commercial buildings can be categorized in this matrix. So if you look at the first one, which is Section J, the National Construction Code, that came into being in 2005, it is a minimum mandatory compliance. It is a compliance that entails a design, energy, efficiency, greenhouse gas rating. And as you all know, probably the National Construction Code is developed by the Australian ABCB, Australian Boards Code, and it is administered individually by the states. So the code itself developed nationally. Then you got the Green Star rating system, which is, again, this happens to be a voluntary rating system. And it is a design rating system that entails greenhouse gas emissions and other sustainability criteria. So it is a combination of greenhouse gas and sustainability criteria, which we'll talk about later in the slides. It is administered essentially by the Green Building Council of Australia, which is a private, non-profit, market-based administration body. Then we come to the NABERS system, which is National Australian Building Environmental Rating System, which back in 2000, almost 24 years ago, that came into being. It is mandatory for many state and federal government offices, because that in fact came into being where government regulation came into being that they lease an office space unless based on a certain minimum performance rating. So to that extent, it became mandatory by the use of state and federal government offices, space leased out from private builders. And then you've got the NABERS could be also a voluntary scheme, depending upon people who want to display their ratings on their own. And then you've got the performance-based rating system, which is essentially NABERS still looks at what your actual performance is. The NABERS rating doesn't look at your attributes, it looks at the actual performance. And the performance could be greenhouse gas emissions, could be water rating, waste, or indoor environment quality. The NABERS scheme essentially being a New South Wales government initiative scheme, but used across all states as well. In 2010, we then had the Act of Parliament, which came into being, which was the Commercial Building Disclosure Scheme, which is now mandatory since the Act was passed in 2010. Essentially entails disclosure, building disclosure, which is a BEAC certificate, Building Energy Efficiency Certificate, that comprises of a NABERS rating, which is a performance rating, and a design tenancy lighting rating requirement. So that came into being in 2010, which is now, and The commercial building disclosure scheme essentially is a transactional scheme whereby it is mandatory to disclose the ratings when a building is, when office space more than 1,000 square meters is for lease, or if the building is at the point of sale. So any of these two transactions will trigger a commercial building disclosure. And it is managed by the Commonwealth government and administered by the Commonwealth government as well. Then last but not the least is the Sustainable SEPP 2022, which actually has increased its coverage, which is for prescribed buildings and state significant development buildings. So the SEPP coverage in 2022 made it mandatory in New South Wales for those prescribed buildings and sustainable state significant development buildings. So, and it was a commitment, the requirement is a commitment to performance at design stage. So that's an interesting one that's now where the rubber hits the road, as we say, administered by the New South Wales government currently.
JS, if I can break in, I think it's important to note that there are more on rating systems available, you know, in Australia and worldwide, but these are the main ones that we see and the ones that we are sort of interested in from the NABERS, the commitment agreement, etc.
Correct. Yeah. And of course, this webinar series really has been initiated to cover, you know, the SEPP 2022 to make it a bit more explicit in terms of, you know, the understanding of energy simulation and its impact in predicting that performance. Okay. So now with the requirement of energy simulation, which becomes a dominant factor, I'll hand over to PC Thomas, who will run you through the aspects related to energy simulation and the more interesting bits and the practical side of what is involved, the aspects of simulation. Over to you, PC.
Thanks, yes, thanks. So I thought the first question we should sort of address is, why do building energy simulation at all? And it's really come about from our interest in energy efficiency in buildings. And typically, we are using building energy simulation to predict the optimal amount of energy use to maintain some defined level of comfort, some definition of comfort. And obviously, we're doing that for buildings that are using systems to provide conditioning. So for air-conditioned buildings, the obvious answer is to look for energy. If we talk about buildings that are not conditioned, then energy is not the issue. We're really trying to look at, you know, how long a space can be kept comfortable. It's not a topic for this seminar, but that's the sort of second reason for using simulation. At that point, we call it performance simulation, but it does exactly the same thing. So when we do talk about comfort, there are a number of parameters that we can say define comfort. However, when we use energy simulation programs, we're really looking at these 4 items, okay? And we're looking for temperatures in the rooms, and these could be air temperatures, operative temperatures, radiant temperatures. We're looking at relative humidity and trying to keep it in a range or not, depending on the air conditioning system we are using. If the spaces are occupied, then there is a mandate to provide some amount of well, fresh air or outside air, really. We're lucky enough in Australia that that is fresh, but if you're in Delhi, outside air wouldn't be considered fresh. And then air movement, if we are looking at air-conditioned buildings, that air movement is governed by some kind of fan or distribution system. If you were doing a naturally ventilated building, then that air movement would be based on how the air is allowed to pass through, either by opening and closing of windows or some particular equipment or system that is made for natural ventilation. Okay, so we're going to concentrate on these four items in terms of defining comfort. Now, I want to spend a little bit of time on this slide. It is the slide, or rather, these are elements of the slides I use when I teach building energy simulation. The reason I want to do that is I find that all of us have got slightly different views of what is building energy simulation, and I think it's good for all of us to be on the same page. Okay, so we're going to start at this bottom corner here. So the first component of an energy simulation model obviously is a three-dimensional representation of the geometry of the building, a digital twin of the building, if you wish. Okay, so in this model that we've got here, these areas that are dark gray, they are all the opaque building envelope. So your walls, roofs, and you can't see them, but floors, ceilings, etc. Right? The light gray bits are your windows. Okay, and we'll talk a little bit more about them in a second. Anything that provides shading from the sun to other components of the building have been highlighted in pink. So just to give you an idea, this is west facing, and on this building there were some perforated screens to keep off the direct west facing sun. So that's why you can see this pink representation here. The building also had a plant room on the top, and they had constructed a tunnel to take all the pipes for the water and the air circulation. Okay, and because it's there, that's shading, providing shading on the roof, and therefore it was modeled as a shading structure on the geometry. Okay, so obviously you can see orientation has been shown here. So this is the north facade. That's the west facade, as we said earlier. Now, once you've got the geometry into the energy simulation model, then you start to describe the constructions. So in this case, I've got here just a section through a wall construction. This one's got an outer layer, an air gap, some insulation, an inner layer. There's also thermal bridging, because the insulation layer has been bridged by some form of structure. In this case, it could be timber, it could be metal, it could be whatever. But when that happens, obviously the effectiveness of the insulation is reduced, and we know how to adjust for that. The code gives us ways to do that. Once you've got all, and obviously this is wall, but then you would do the same for roof, internal walls, floors, ground floor, internal floors, etc. The next thing which is quite important in its description, is how we describe the performance of windows, of transparent parts of the building, because solar radiation comes through that part of the building. we are interested not only on the glass part, but how the frame of that system, of the window system, affects the performance of the window system as a whole. So you will find that there's some quite complex ways of calculating those performances. Now, in terms of the construction systems, we are interested in what we call an R value, a resistance to heat flow. And obviously, all the models nowadays, particularly the ones that have gone through the ASHRAE SPC 140C best test, will work out the impact of thermal mass. So each of these layers would have a defined, the mass would be included as part of the specific gravity of the material. Okay. In this case, we are interested in 3 performance parameters. How does the window control how much sunlight is coming through? How does the window control how much daylight is coming through? And then instead of R values, as you know, we use U values, which are the inverse of the R values. And that gives us an idea of how the window controls for heat gain or heat loss, depending on what the temperature differential is between the inside conditions and the outside ambient conditions. So that is quite an important part of our energy simulation model. Another thing we need to do is we need to divide the simulation model, and I've got a plan here of one of the floors of this building over here. You can see that there are certain lines. So we talk about perimeter zones, which are close to the external wall and typically are about 4 meters or so deep. Okay. And then we talk about interior zones. So the blue zones are all internal or interior zones. And then we talk about unconditioned zones. So in this case, staircases, toilets, etc., plant rooms, anything that you can see in white, these are unconditioned zones. Now, this zoning is not necessarily the zoning that might have been anticipated by the architect. In fact, the architect is really not interested so much in thermal zones. He's interested in spaces, right? We as modelers are interested in thermal zones because we describe them as being areas which have got the same kind of activity happening in the zone. And that might be that they are occupied in a similar way or the same kind of function happens or whatever. The mechanical engineer will decide how he's going to condition these areas. So in this case, this is a floor-by-floor system. You can see the air handlers are over here. This air handler is conditioning that zone here. You have a second blue air handler, which is conditioning both the interior zone and in this case, the majority of the south-facing zone. And that's because the engineers decided that there's not a lot of direct solar radiation, so it should be close to how the internal zone works. Okay. Now, this line here, which separates these two zones, it's not a physical wall. It's a wall it's an arbitrary wall that the air conditioning engineer has decided he's going to use to split these two areas apart. We model them as virtual partitions, so not real partitions. But there is a system here, an AHU that deals with this space. There's another AHU that deals with that space. Okay. So this is another input that we need to provide fairly early on in the simulation model development. So once you've got all these things, most of the geometry is kind of covered, then we start to think about all the things that might cause a building to become uncomfortable. We call them building loads. Okay. So you have solar radiation. That's a major heat load, particularly in Australia. We have a lot of sunshine. So then how it comes through the transparent part of the building envelope is very critical. That's one big building load. Then, as we said, there is a heat gain or heat loss because of the construction of opaque building elements. And that decides how the temperature on the outside and the sunshine that's falling on that opaque construction actually comes into the space or gets lost from the space if it's a cold ambient condition, and how slowly or how fast it does. And that's determined by both the U value and those material properties which decide how thermal mass in the building works. Okay. Then we have a series of loads on the inside. So the three ones that we normally consider in office buildings are people loads, lighting loads, and equipment loads. And I'm sure you all know how that all works in the NCC. The thing to kind of point out is that when you look at people loads, you have two or three things to consider. People generate heat. All of us are equivalent to about 100 to 130 watts of continuous heat generation. So the number of people in a space matters. Then we're using computers. With the people, you have to provide ventilation air. Otherwise, you risk people getting lethargic and worst case scenario, suffocating. But that is again dependent on people. And then for people, we also, the heat load that we generate is not purely sensible load. We also generate some latent or moisture loads that the air conditioning system needs to take care of. Okay. Equipment loads, computer loads, fax machine loads, whatever else is in your office building or other building which is producing heat, provides sensible loads to the buildings. And within the NCC, there are limits to how much you're allowed to use. So for lighting, for equipment, and for people, these things are specified depending on the type of the building you are using. Okay. Now, the last thing to think about is how air exchange happens in a building. So the air brings with it heat and moisture, or takes away heat and moisture, depending on what you're doing. So we have what we call ventilation load. So that is something that the engineer decides he has to provide because there are so many people in the building. And usually that's codified. We typically use 10 liters per second per meter squared, but there are changes, as you know, depending on which rating scheme that you might decide to follow. Now that is something that we hope to control. But there is also infiltration or leakage into the building and out of the building. When a fan runs, it pressurizes the building, so infiltration rates are low. When you don't have a mechanical fan running, obviously that's wind-driven infiltration. And the model has to differentiate quite carefully between these two. So those are all your loads that are causing the spaces within the building to become uncomfortable, either by becoming too warm or by becoming too cold. And that's what you're trying to model. Okay. Now we have specified all these loads. We also need to see how these loads actually are operated during the day or applied during a day during the weekend on the building model. So I've got here a spreadsheet representation, a graph of how occupancy is modeled in the National Construction Code, right? And what you might see, I'm sorry, the graph is a bit small. I was just trying to keep it all in one graph. But what you'll see in the schedules that are there for the NCC is that occupancy is modeled to be 70% of a potential 100%. Okay. So why that's important is that when the mechanical engineering is designing his air conditioning system, he is designing it for full occupancy, 100% occupancy. He's sizing it when all the lights are on, all the computers are working, everybody's on their seats, and it's a really bad, really warm day for cooling systems. That's what you're doing. A design day, as it's called. Okay? But the code recognizes that that's not really how buildings work. Typically they expect about 70% of the design population to be there on a working day. And so that schedule or profile has been defined for us. And we have profiles for how lighting works, when the air conditioning is switched on, when infiltration increases and decreases, and so on. These are all parts of the building energy simulation model. The reason I'm going into it in such detail is if you've come from a background where you've been using NATERS or CHINAT for simulation, MERS Pro, Accurate, First Rate 5, whatever it might be, Hero. Many of these things are hidden and locked down. But when you do a large building, the models that you use are much more flexible and you have access to all of these things. And with that flexibility comes the responsibility for you to ensure that your models are accurate. Okay. So here, these are operational schedules. Now, one of the things to think about is that when you are doing a model, we're sort of assuming that the building operates in exactly the same way Monday to Friday, every day, every week of the year. And that's not how real buildings work. So that is then starting to, cause some differentiation between what we are using to predict a number and what might actually happen in the real world. And we need to be mindful of that. Okay. So this has got now everything in our model except the mechanical systems. We've defined the lighting systems here, the equipment systems there, the schedules of operations there already. We are down to having to put in a conditioning system. In an air-conditioned building, obviously, we're talking air conditioning systems. So again, I've got a very complex graph put into one slide, and I apologize for that. We can do, more detail when it's required. But here's the zone that we are conditioning. One of the zones that we are conditioning. One of these areas that is in the model, right? And you can see a number of loops. So this is what I call a Rolls-Royce air conditioning system. It's a water-cooled, chilled water system. I guess this could be a VAV type system. So we have an air loop, and the air loop is the thing that supplies cool air for cooling the space. Once the heat in the space has been picked up by this air, then it is returned. And on the process of return, some of it is exhausted, and that is replenished by this ventilation air or outside air we talked about. And then the combination is filtered, goes past a cooling coil, which makes it cold, goes to a fan, which is blown. This is one configuration. There are n number of configurations for air conditioning systems. So here's your air loop. Now, obviously, for that cooling coil to become cold, it needs to be provided with chilled water in this case. That chilled water is generated by, in this case, a chiller The chiller is represented by a compressor, a condenser vessel, an expansion valve, and a evaporator vessel. It all comes in one big piece there. It provides chilled water, which is pumped around the circuit that cools this cooling coil. In the process of making chilled water, there's work being done by the compressor. And so the chiller gets warm. That needs to be cooled to keep it operating efficiently. So all of the heat that is pulled out of the zone and picked up because of the inefficiencies in the system are dumped into the condenser vessel. And from the condenser vessel, in this case, it's a water-cooled system, so there's a cooling tower. So condenser pumps push that water to the cooling tower. The cooling tower is essentially just a shower. It's a spray, and as the spray comes down, some of that water evaporates. Water has a very high latent heat capacity, so that cools the water in the cooling tower basin, and that keeps the cycle running. Okay, so typically in an air conditioning system, you're picking up heat from an already cool space, and then you're dumping it into the atmosphere. You cannot destroy heat. It has to go somewhere, law of conservation of energy. So you pick that heat up and then you dump it into the atmosphere. So every time you cool, you are kind of heating the atmosphere if you want. Okay. So this is your total energy simulation model. There is another loop which we haven't shown, but that is the controls loop. And that's very critical in your energy simulation model. How do you decide how to control the system? Why do you need to control the system? Well, when you sized it, say you had 1,000 kilowatts, but that 1,000 kilowatts is for the design day when the outside conditions are very warm, and when you assume that everything is going flat out. So all the people who occupy the building as per design are there, they're doing what they're doing, all the lights are on, all the equipment is running, etc. And by definition, you only need that for about 1% of the year, because that's what a design day definition is. Which means that for 99% of the year, you don't need 1,000 kilowatts, and your control system needs to back off the air conditioning system in an efficient manner for the rest of the year. That's what the building energy simulation is trying to model. That's what an energy efficient air conditioning system is all about. So now that you've built your simulation model, what do? Well, you need to then make your energy simulation model respond to a climate file. And typically we use something called a reference weather data file. So somebody has looked at it and said, yes, this is fairly typical for the place. And obviously now we are thinking of future weather files or current weather files. There's a lot of discussion about that. Your building model is made to respond to this climate file, and there is a calculation engine, a simulation engine. And here I've shown you design builder software model, but the engine underneath that is Energy Plus, made by the US Department of Energy, of course. And what you are hoping to get at the end of that is, once you've run the simulation, we're looking for an energy use breakdown by system. So you can see here cooling energy in the blue across the year, and so on for all the other systems that I'm interested in. Okay, so that's the energy modeling process, and that's what we are using for all our rating systems so far. So if you go from there and then start to look at how energy simulation kind of intersects with the rating process, if you're looking at section J, compliance, one of the verification methods we use is J1 V3. It used to be called JV3. In 2022, they've called it J1 V3. And that's the most commonly used one in industry. And typically we use that to test facade compliance. Now, there are other things that, other ways to comply. We'll talk about that in a second. But this is the most commonly used one in Section J. Okay. And we use the building energy simulation programs to predict the theoretical HVAC energy use. If you start looking at green star ratings, then energy simulation is used for the energy credits, so energy or greenhouse gas emission credits. And again, we are predicting a theoretical set of numbers for that, unless you use the NABERS pathway. And if you, in green star, but there's also a straightforward NABERS pathway in Section J. We use that a lot. And NABERS has got commitment agreements for whoever wants to commit to a building performing at a particular NABERS rating after it is built, and once you've collected 12 months worth of bills, once the building has been occupied to a particular level. These things you all know, but I'm just reiterating that. But here what happens is that when you start to use energy simulation for NABERS, you don't use it to model a theoretical number. You try and use it as a risk assessment tool. So unlike when you use it for Section J or even sometimes in green star ratings, you're not trying to get a particular number. You're not trying to get 100 megajoules per meter squared per year. You're trying to say, well, what is the worst case scenario so that I will still get my NABERS rating? That's why we do things called off-axis scenarios when we do ratings, energy simulation studies for NABERS. Okay, so let's look at each of these in a little bit of detail. Okay, so compliance with the NCC, we all know what that is about. You have performance solutions, you have prescriptive solutions, you can mix and match anything you like. We're really interested in these verification methods. And in 2019, there were 2 additional verification methods that were proposed. Okay, this is now called J1V1 in the 2022 code, and that is via signing a commitment agreement. So essentially you go and you go to the NABERS team and say, yes, I commit to ensuring that the building will perform at a whatever star rating it is that the code requires you to perform to, and then you go through the usual commitment agreement process. So there's a quality assurance set of checks. You have to build a simulation model. The reviewer has to look at both the design and the simulation model and suggest whether you've got a good chance of achieving that rating or not. You also have a route using green star. So you can, instead of showing compliance using JV3 or the prescriptive method, you can then take a certified, you can certify or register your project with green star and design an as-built, and then go through whatever energy pathway you choose to within the green star tool. Okay. If we talk about the JV3 method, okay, because these are all the verification methods in the 2022, we won't talk about the last 2. That's a blower door test. This is for apartments. What you'll see is that for JV3, there is a bunch of additional requirements that you will find, okay? And really, it's these 2 that we are looking at. So for compliance with Section J, if you're doing building energy simulation. Then specification 34 gives you all those schedules for occupancy, schedules for lighting, when is the air conditioning on and off, how people occupy the place, what's going on in there. Okay, that's all provided for you here. Okay. The code also says that if you feel that your building is operating differently and you know how it's going to operate, you're allowed to use those schedules instead of what's provided here. Okay. So you have modeling parameters and modeling profiles all provided to you. There is also a good description. I think we've got time, so I might just quickly zoom out and have a look at that. You'll find there's quite a detailed description on what's happening in how you model systems. So if we go to modeling parameters, and this is the online version of the code, I'm just going there. You'll see here there is a description of what needs to go into the reference building. There is a description of what needs to be done for both the proposed building and the reference building models. So they need to have exactly these things here. There are descriptions of things about the building envelope, and there is a series of things about systems. So it starts to talk about how you need to model air conditioning system. So sequencing of different kinds of, so if you've got multiple chillers or outside condensing units, how you need to control the air conditioning systems, what is possible, what is not possible. If you can't simulate it, what do you need to do, etc., etc., etc. So there's quite a lot of detail provided for us in terms of how we need to model. And you can see that in 2022, there's been quite a lot of addition. 2019 actually did that. 2022 repeated that. There's all kinds of things about part load performance and how you must stage it and how you control the chill water temperature and so on and so forth. I'm sure many of you already know how to do that, but I'm just bringing it to your attention again because it's part of the energy simulation process. So let me go back here. So that's our JV3. The actual description or problem statement, I guess, for JV3 is given here. So typically you are trying to model a reference building, which is code compliant, and then you are also testing the performance of your proposed design against this reference design. Now it says that your proposed building emissions must be equal to or less than that of a reference building when, and then you have these two clauses here. Now, typically in the industry, what we've been doing is that when you're trying to set up the facade, you are looking at this clause, number 2 clause. Okay, so 1, 2, and you are using a reference system. And you're modeling the reference system here as well, but you are changing the building envelope. That's how you show compliance with the building envelope. Okay. And because there's an and, you need to model thermal comfort. And so we have this whole thing about managing PMV for the occupied zones. And the reason for that is because your building facade can never be an uncomfortable facade. You have to have a comfortable facade for your building, even if you decide to put a big solar system on the roof and generate lots of green power, which you are using on site. Okay, you can't obviously account for anything that's sold off to the grid. You can only account for what's being used within the build. And then there is a requirement that whatever simulation tool or software you use must comply with this ASHRAE standard 140. It used to be called Bestest many years ago. Now it's become a standard that we use. Okay. So one thing I wanted to point out is by this time you would have recognized that even for JV3, you have to model a fairly detailed air conditioning system. You can't do a theoretical, simple HVAC system. That is not allowed. And that's typically because when you are testing thermal comfort, real systems take a little while to get up to speed. And the first couple of hours, if your system is not well controlled, you may lose thermal conditions over there. And there's some fairly, clear definitions in the code as to when you are testing for thermal comfort. I won't go into that right now. Okay, so that's a quick look at section J. For Green Star, as you know, there are a bunch of tools available. We're really interested in the building tools, so the design and as-built tools. That's what we're looking for. And within Green Star, there's a number of sustainability indicators. Again, we're looking at the energy/greenhouse gas credits. And in those credits, typically, what you're doing is using simulation. You have to ensure that your building is better than a reference building or equal to a reference building. And that reference building is not the same reference building as the section J. It's usually something better. And, you can read about that. And this model must include a well-defined mechanical system. In fact, within Green Star, depending on what the size of your building is, they have already provided a description of what the reference building needs to be. And unlike JV3, you have to include all systems that are required. Within JV3, you need not model those systems, but whatever you do, you've got to do the same for the reference and proposed buildings. Okay, so that's the way Green Star and building energy simulation work. So finally, when you come to NABERS, if you look at NABERS, Ryan went through this last time. You have a 6-star energy greenhouse gas performance scale. NABERS started by developing benchmarks for offices and then went on into hotels, data centers, etc. There's a chart in the next slide. We'll look at that. And again, that's one that Ryan has presented before. You therefore have to calculate your energy rating based on utility bills, water as well. So you need to have the bills to do that. And so it becomes a performance rating using historical data. It's not a predicted rating anymore. You might have used a prediction tool to sort of estimate what the energy use will be, and that's what the NABERS Commitment Agreement process is all about. But your actual rating is based on bills. Okay? So we have a commitment agreement pathway because developers decided that they needed to be in on the action. NABERS was originally built for existing buildings. So they came along and said, how do we get, how are we able to market a building that is not yet built? And NABERS said, yep, can do that. Sign a legal agreement with us. Promise to ensure that your building will work at this NABERS target once it's up and running and we've collected the bills. And so you use energy simulation to do that work. These are the areas that NABERS is working on. The first few benchmarks were developed for offices, both base building and tenancy and whole building, and then data centers, hotels. And then There are so many other systems now in place. These are coming soon. We are really interested in the three that are offices and hotels. These are prescribed in the SEPP, which we'll come to in a second, and also for common areas in apartment buildings. Okay. So when SEPP came along, oh, sorry, before I do that, just a quick look at the commitment agreement process. Again, I'm using the same figure that Ryan used in the last seminar. We're interested in this part where we use the energy simulation model using the NABERS handbook. It tells us what all is required in the energy simulation model. And that's part of the commitment agreement process. So when you come to SEPP, the new SEPP has basically for the first time said the energy standard is going to be a NABERS rating, which is immediately saying that it's not about design, it's about what your building actually does. They have defined prescribed buildings. There's also states significant developments, which I haven't mentioned here. But a prescribed office, as you all know, more than 1,000 square meters, now needs to commit to performing to a 5.5-star NABERS. Hotels need to commit to a 4-star. Apartments, the common areas of apartments need to commit to a 4-star, right? So for the first time, we now have at a development application type stage, having to commit to an operational rating, which will be monitored by the state government. And obviously, we are using building energy simulation tools to try and predict the future, to try and predict operational performance. Okay. So there are some large differences between when we use JV3 for doing simulation and what we need to do to try and predict operational outcomes for NABERS. Okay, we'll deal with that in detail in the next webinar. That's all we're going to deal with. But just to give you a preview, you have to now start to account for all systems that consume energy. Okay. And you'll find that you can't account for all of those systems in the energy simulation model. So you got to have some other ways of computing that. Sometimes it's a model, sometimes it's just an Excel spreadsheet, and you're trying to estimate what those systems would be consuming into the future. Okay. One of the things that me and GS are always looking for, particularly when we do an independent design review for commitment agreements, is that we want to ensure that whatever inputs you put in the model has to be practical, and it has to be robust. Your system, when you test it in failure modes, should still be able to achieve the NABERS rating that you're targeting. So we are kind of quite interested in that. Okay. One of the things we find is that building services are modeled not as well as the building envelope. I guess we've got a long history of being able to model building envelopes. We are not so yet expert at modeling building services. Typically, it would be good to have some mechanical knowledge to be able to model air conditioning systems, particularly if you're modeling large, complex systems. It's quite advantageous if you have some mechanical design, something in mechanical systems that you can do simpler systems without too much difficulty. So if you're doing a split system or a VRF type system, that's not so difficult, but larger systems become quite complex. And then The models are not perfect. There are certain things that they can't do very well. There are other things that they can do very well. So when you are doing energy simulation, you need to be aware of the limitations of your modeling software. So these are the things we're going to cover in the next webinar. I can see Ryan's come back online, so I will hand over to him to look out for any Q&A and other questions we might have. Let me just check that I am on the last slide. Yep. Okay, go ahead, Ryan, all yours.
Thank you, PC. It looks like we've reached the end of our allotted time. It's 3 o'clock, so I see that there are some questions here in the question and answer section. What we'll do to make up for that is that we'll follow up with you all following the end of this session. So if there's anything that we may have missed, we'll be able to answer you following the session. And if you would like to, we will also be discussing all of these aspects that PC covered on this slide at the moment in the next session. So really hope to see you there. And with that, I'd just like to thank everyone for attending this afternoon and hope you all have a great day. Thank you.
Thank you. Thanks, Ryan. Keep your questions for the next session and we'll answer them.
Thank you.